Hello friends, welcome to this video on number system. In the previous video, we learned about rational and irrational numbers. In this session, we will learn about decimal expansion of rational and irrational numbers. Friends, can you identify the rational and irrational numbers from these numbers? We can easily identify them by simply taking note of the definition. So these are rational numbers and these are irrational numbers. All given rational numbers are in the form of fractions. Can we write them in decimal form? Yes. For that, we will have to solve them by the division method. Let's take the first example 5 by 4. Here, we will divide 5 by 4. We get the answer as 1.25. In this example, after a few steps, the remainder becomes 0 and the decimal expansion in the quotient ends. Therefore, this decimal expansion is called terminating decimal. Now let's take the next example 10 by 9. Here, when 10 is divided by 9, the remainder 1 is repeating instead of getting a 0. Similarly, in the quotient also, 1 is repeating and its decimal expansion is continuing in form of 1.1111. If you observe it carefully, it is a never-ending process. A decimal expansion where both the remainder and the quotient are repetitive is called non-terminating or recurring decimal expansion. We can also write it as 1.1. The bar above reveals the group of digits that recur. If we look at the third example, 1 by 27. Here too, the remainder is not 0. If we look at this division carefully, after the third step, we are getting the same remainder again. If we solve this further, then the same 3 steps are being repeated. And now if we look at the quotient, then we realize that just like there is repetition in the remainder, there is a repetition of 037 group of digits in the quotient after the decimal point. So can we call this decimal expansion also non-terminating or recurring? Yes. And we will write it as 0.037 bar. Friends, can you tell what is the difference between examples 2 and 3? In example 2, only one number is repeating. But in example 3, a group of digits are repeating. If we compare all 3 examples, we can say that in the decimal expansion of rational numbers, after a few steps, the remainder either becomes 0 or starts repeating itself. The numbers in the remainder are always less than the divisor. Like in example 2, 1 is getting repeated and the divisor is 9. In case of example 3, there are 3 blocks of repetition and the divisor is 27. Friends, so far we have seen the decimal expansion of rational numbers. Can we write irrational numbers also like this? Let's see. The decimal expansion of root 2 and root 5 is as follows. If you look at them carefully, the numbers are neither being repeated here nor are they ending. Likewise, we can find many irrational numbers and write their decimal expansion. You must be familiar with pi. Its decimal expansion is also like this. Here also, the numbers are neither getting repeated nor are they ending. Thus, we can conclude that the decimal expansion of irrational numbers is non-terminating, non-recurring. Friends, can you write an irrational number like this? Yes, we can write many such numbers. Friends, that's all in this video. In this session, we learnt about the decimal expansion of rational and irrational numbers. See you in the next video. Thank you. Hello friends, welcome to this video on number systems. In the previous video, we discussed the decimal expansion of rational and irrational numbers. Today we will solve some questions related to the same. Let's start with the first question. From the given numbers, identify the rational and irrational numbers. You can pause the video to think about the answer to this question. In the first and fourth numbers, no digit or group of digits are getting repeated after the decimal. And the series of points next to them shows that they don't end, that is, they are both irrational numbers. In the second number, the bar above 5 indicates that 5 is being repeated here. And in the third number, the group 847 is repeating after the decimal. Therefore, they are both rational numbers. Friends, let us see this question. Write the given fractions in their decimal form, their decimal expansion. First fraction is 48 by 100. We will write it in this way and solve it using the long division method. Here, the remainder becomes 0 and its decimal expansion is 0.48. Therefore, it is a terminating decimal expansion. 1 by 16. On solving this too, the remainder obtained is 0. Its decimal expansion is 0.0625. Therefore, this is also a terminating decimal expansion. Friends, the third fraction looks slightly different. It is 3 1 by 6. 6 multiplied by 3 plus 1 is equal to 19 by 6. On solving this, we do not get the remainder as 0, and after 2 steps, 6 is getting repeated. Hence, we get the decimal expansion as 3.16666. Therefore, this expansion is non-terminating, recurring. Friends, let's look at the next fraction 29 by 99. If we solve this, we realize that the remainder is not 0. In the quotient, 2 and 9 keep repeating themselves, and the decimal expansion is 0.292929. We can also write this as 0.29 bar. Friends, upon looking at it, you can easily say that this expansion is also non-terminating, recurring. Friends, till now we converted fractions into their decimal form. Can we convert decimal form to fractions? Yes. Now, let's solve some questions related to the same. Express these numbers in the form of fractions, where p, q are integers and q is not equal to 0. There is a method to solve these type of questions, which we will see in the next few steps. Let's take the first number, 0.888. Let's consider it as x. Now we will see whether a number or a group of numbers is repeating after the decimal. Here, the same number 8 is getting repeated. So, we will multiply both sides by 10. After multiplying, we get 8.888. That is, the decimal went one step to the right. Now we can also write it as 10x is equal to 8 plus 0.888. We have assumed 0.888 as x, therefore it will be 10x is equal to 8 plus x. 10x minus x is equal to 8. After solving this further, we get x is equal to 8 by 9. Friends, let's take the second number 0.27. It is very easy to write it in the form of a fraction. This is a terminating decimal expansion. There is no repetition of any number or group of numbers. Here, because there are only two numbers after the decimal, we will multiply by 100 and divide by 100. And now we will get 27 by 100, which is the fraction form of this number. Friends, let's take the third number 2.2424. Let's consider it as x. In this number, two numbers that is 2 and 4 are getting repeated after the decimal. So here we will multiply by 100 and solve it in this way. We get x is equal to 222 by 99. Friends, that's all in today's video. In this session, we solved some questions related to the decimal expansion of rational and irrational numbers. See you in the next video with some facts related to this. Thank you. Hello friends, welcome to this video on number system. Today, we will discuss some facts related to the decimal expansion of rational and irrational numbers. Let's get started with a question. Show 1 by 19 in the decimal form. Here, we will solve it by using the long division method. Friends, look at the quotient. We have not yet got any repeated number or group of numbers. So, is this an irrational number? Let us solve it further. Now look at the quotient carefully. It is getting repetitions of numbers after 18 digits. You can also write it like this. After looking at this, we can conclude that if you do not receive repeated number or group of numbers after solving the fraction for many steps, it does not imply that the numbers will not get repeated at all. We can write this number as 1 by 19, that is p by q. So it is a rational number. In this, we will definitely get repetition of some number or group of numbers. Friends, that's all in today's session. So in this session, we discussed some facts related to the decimal expansion of rational and irrational numbers. See you in the next video. Thank you.